We're starting section 3.3, the product and quotient rules for differentiation. First we do the product rule, then we do the quotient rule, and we give examples. One thing I want to warn you about, with limits of a product of functions is equal to product of the limits of functions if the limits exist, and limits of quotient of two functions is the quotient of the limits if the limits exist and limits of denominator is non-zero. So this sometimes causes a confusion with the differentiation rule. With differentiation rule, you cannot just go back to those two laws and replace the limit with differentiation. Differentiation rules have different formulas to use. So that's one warning, little fair warning in the beginning to remember. We have to memorize the two formulas here. So first thing, we try to derive or prove the product rule or a product of function rule. And so what is the significance of doing this? First of all, we derive the formula once and we don't have to go back to it in this course. But what happens in your future is that you have to take upper mathematics courses in engineering and science. If you're continuing with engineering and science, and in those courses, there would be proofs that has to be done. There will be proofs that have to be done, and getting basically familiar with proofs right now and understanding it helps you create your own proofs in those courses. And so we start from here. So let's try to find a formula for differentiating a product of functions. Even though we know that the limit law is not going to be similar to the product rule of differentiation, we're doing a similar process. In limit law, we connected the product of the limit of product of two functions to limit of the two functions. Here we're going to connect the derivative of product of two functions to derivative of each function itself and the functions themselves. So where we start is in this page is about driving the formula. Driving a formula, and we were going to do it once and not come back to it in this course. But in your future, you will be, if you're continuing with your plan with science and engineering, what happens is that in your future math courses, you are going to be, you're going to have to prove statements in mathematics. And becoming familiar with them right now is useful for you in the future and makes you a stronger student then. And so now let's start to try to relate the derivative of a product to relate it to the functions and their derivatives themselves. First, the product fg is defined by fg of x equal to f of x times g of x. And suppose that f of x and g of x are both differentiable functions. What is fg prime of x? I don't have a whole lot of knowledge right now about fg prime. All I know is that limit definition. I know limit of fg x plus h minus fg x over h as h approaches 0 will give me the derivative of fg prime. Now, what is fg of x plus h? I can replace that by limit f of x plus h, g of x plus h, minus f of x minus times g of x. This one is times. Divided by h as h goes to 0. Now, what is the goal? So this was just writing the limit definition and then writing it as the actual product, and now I can't quite see the derivative of the either of the functions, but I can also separate this in a way that to be able to see the derivative and the function separately. What I know is maybe I can regroup things so they end up to contain the function and derivative, and I can get rid of the limits. But I mean, basically, instead of having the limit and computing this all the times with the limit definition, maybe I can find a formula, and as we did in 3.2. But it's not as easy to see. It becomes a constant trick that will follow in upper mathematics, that you add and subtract a certain term, and which makes the keeps the expression the same, but that constant term can regroup with either of these groups over here and help you see connect these things to the derivative of f and derivative of g and f and g by themselves. So those terms are, the term that we're adding and subtracting is f of x plus h times g of x, and so I add and subtract, which makes it 0, which makes the original expression the same because I added 0 only. Then when I do this, I notice that I can actually, this term that I add and subtract has one common term with this side, and one common factor with this side, and one common factor with that side. So now what makes sense is to basically factor that common part. So I'm just putting this part and that part. So I factor x plus h out of it, and what am I left with is g of x plus h minus g of x divided by h. And then I will have, if I factor g of x from there, I get g of x times f of x plus h minus f of x over h. Now I notice this is promising, because if I can bring the limit in here, which I can, and bring the limit over here, which I can, then I see the derivative of g and derivative of f. And then I see g over here, but I also see f of x plus h. So what happens is that because this is a product, limit of product is product of the limits. So I can write it as limit as h goes to 0 of f of x plus h times limit as h goes to 0 of this entire thing. And that's just the noticing that since f is as continuous, f of x plus h as h goes to 0 is just plugging in h in here. Direct substitution gives you f of x. So this is f of x, and this is going to be g of x. What about this part? This part, when I distribute the limit, g of x is a constant for this limit. Why? Because it's h going to 0. So g of x stays outside, and then I will have limit as h goes to 0 of f of x plus h minus f of x divided by h. And this one actually is the derivative of f prime. So we will have f of x times g prime of x plus g of x times f prime of x. That's the answer. The formula becomes f of x times g prime of x plus g of x times f prime of x. Two terms, in each term, it's one of the functions times the derivative of the other one. And that's the formula that you have to memorize for the derivative. One little thing that I want to mention, when we said limit of f of x plus h as h approaches 0 is f of x, this is true because f is differentiable, and when a function is differentiable, it's also continuous. So the product rule, to summarize what we did, if f and g are differentiable at x equal to a, then we have just proved that 1, the product f times g of x is differentiable at x equal to a. 2, fg prime of a is equal to f of a times g prime of a plus g of a times f prime of a. And this was Lagrange notation, and then Leibniz notation, the derivative with respect to fg of x, derivative of fg of x with respect to x evaluated at a is equal to f of x derivative with respect to x of g plus g of x derivative of f with respect to x, and the entire thing evaluated at x equal to a. Again, both Lagrange and Leibniz notations are here, and this one, so you can compare, but it's always they're always make of two terms. One term has the one of the function itself and derivative of the other. The other term has the function whose derivative was here times the derivative of the other function, and so they switch their place in each term. And these two equations are the same. There's just one is in Lagrange, one is in the Leibniz notation. Again, the product rule, this is what you need to memorize. A lot of people find the Lagrange version of the formula easier to memorize. If f of x and g of x are differentiable at x equal to a, then fg of x is differentiable at x equal to a, and fg prime of x is equal to f of x g prime of x plus g of x f prime of x. Now let's do a few examples on this one. Example 1, find the derivative of the product 4x minus 3 times 3x plus 4. I want to remind you that if you actually, this is a question that can be done with the knowledge in 3.2, but it's easier to use the knowledge in 3.3 to actually do this problem. How do I do this with knowledge of 3.1? You just FOIL these two and then take the derivative. So let's get, so according to the product rule, what I need to do is, let's see, this would be, let's say, f of x, and this one would be g of x. So I take the derivative of, let's say, f of x. I can, either term can come first, right? Derivative of f of x, a derivative of 4x is 4, derivative of negative 3 is 0, so it's 4. Then I have to multiply it by g of x, which is 3x plus 5. Then I write f of x, which is, now I'm doing this term, 4x minus 3. Then I multiply it by derivative of g of x. Derivative of g of x, 3x is just 3, and 5 is 0, so I get that. Now I can, after I did a product rule, I can multiply through and clean it up. Or for the matter of gateway exam, you can just keep it like that and not do anything to it. But cleaning it up is 12x plus 20 plus 12x minus 9, that's 24x plus 11. So, and I mentioned something about this was doable without the product rule. Yes, I could have written it like this. Foiling it through, I would have gotten 12x squared, and then 5 times 4, 20 minus 9, 11x minus 15. And that derivative of 12x squared is 24x, and derivative of 11x is 11, derivative of negative 15 is 0. And see, both ways you get the same answer. So why to use product rule? Because when things are more complicated, just multiplying, foiling it through is harder. And there's another reason. There are functions that are not just polynomials. And then how do we take the derivative of those? And so let's say I multiply e to power x by a polynomial. How to take the derivative of that? So it has its own merits, and also it can be used with in conjunction or instead of some other methods. And so now the next question is take the derivative of square root of x times x squared plus 1. Again, according to the let's say the product rule, and this is f of x, and this one is g of x. Let's say f of x times the derivative of g of x. Derivative of x squared is 2x. Derivative of 1 is 0, plus derivative of f of x, which is going to be, what is square root of x is equal to x to the power 1/2. That's the first step that I want to take. I want to convert square root to power because I have the power rule. So derivative of square root of x is 1/2 x to the power negative 1/2 times g of x, x squared plus 1. And so I can clean it up a little bit like this. X squared plus 1 on top, and bring the 2 out. 2x square root of x. By the way, 2x square root of x is just, you can put that together, or first you can take care of this part because there's a square root of x in the bottom. And so that finding a common denominator or using other kind of methods that we showed you with factoring, you get 2x times x plus x squared plus, 4x times x. Square root times square root is x, divided by 2 square root of x. And so 4x squared plus x squared, that's 5x squared plus 1, divided by 2 square root of x. So other questions that comes in mind is that was this the only way to solve this one? This one is not the only way neither. Let's say instead of doing this, I convert x to the square root of x to x to the power 1/2, and now I FOIL before I take the derivative. What is x to the power 1/2 times x to the power 2 is x to the power 5/2. What is x to power, and then plus x to the power 1/2. Derivative of the first term, 5/2 comes down, x to the power 1 less, 5/2 minus 1 is 3/2, plus 1/2 comes down, x to the power 1/2 minus 1, which is negative 1/2. Oh, but and now I can use the method. It's easier to see why sometimes we use the method of basically factoring the lowest term. And so when I factor the lowest term here, it's x to the power negative 1/2 between the x to the power 3/2 and lowest exponent, I'm sorry, and x to the power 3/2 and x to the power negative 1/2, and then I have to factor 1/2, so I get x to the power negative 1/2. What is remaining out of that one is 5, and because this is divided by x to the power negative 1/2, it would be x to the power x to the power, it would, so it's 3/2 plus 1/2, which is 4/2, which is 2, and then over here what is remaining is 1, and that's exactly the same thing as we had over there in a different format, basically. So far we did 2 derivatives that you can use other methods with, but now we're doing another one that you cannot use other methods with. How do I take the derivative of this one with the methods that I know other than product rule? We can. So let's try to actually use the product rule. Let's have this as f of x and this one as g of x. So derivative of, let's write x times derivative of g of x, which f times derivative of g of x, which is going to be derivative of e to the power x, if you remember, was e to the power x times natural log of e, which is 1. So it's going to be e to the power x. Then add to g of x, which is e to the power x, times derivative of f of x. F of x is equal to x, therefore derivative of that is 1. So it's going to be e to the x. You can write it like that, or you can write it as this with a factoring. This is good enough for the gateway exam because we're just learning how to take derivative. Later in the semester you will need that.